Okay, so in the lab tonight, I'm going to tell you a couple of different things. This first video is going to be sort of very simple. All I'm going to be doing is implementing the the biconjugate gradient stabilized BiCGSTAB, and then also the conjugate residuals. So both of those are things. Well, I've uploaded notes for both of those things. The book does not do. I mean, the book. I think on these points it does not do a great job deriving the algorithms or explaining where various things come from. And so because of that, I uploaded notes instead of having you read the book or instead of making videos, just because, as you can tell from the notes, things are very technical, and sometimes it's not the most fruitful thing to show that on the board. So instead, what I'm going to do is show you how we can code some of these things. But I would suggest, I think you probably have to, if you want to follow along with the algorithm here, you should be looking at, what am I trying to say here? You should go to the notes that I uploaded so you can see the algorithms, because I'm going to be referring to them, but I'm not going to have it on the screen here. Or maybe I can. Let's see. I guess this is definitely something I could do. Hold on one second. Wait, what the heck? That's not what I meant to do. Okay. Sorry, I'm just trying to. Here we go. Okay. Well, here we go. Final. Nope, almost. All right. So you should. I'm bringing the window over. This is the algorithm for BiCGSTAB right here. But that's going to happen, isn't it? Here we go. Well, that'll work, won't it? Okay, so this is the BiCGSTAB algorithm over here. What I have here, and I will make this available to you guys. This is the make large 3D problem. We have that. We've seen that before. And then I just have some code here that I didn't write to make a random sparse matrix of dimension n by n. Okay, so I'm going to begin by doing the BiCGSTAB algorithm. So this is going to look and form very similar to the conjugate gradient algorithm, because it's sort of a well, you have the conjugate gradient, then biconjugate gradient, then conjugate gradient squared, and then this algorithm. It doesn't just, conjugate gradient, the matrix needs to be symmetric, positive, definite. For BiCGSTAB, it can be anything. Doesn't have to be symmetric, doesn't have to be positive, definite. So we're going to also see how we can precondition this a little bit later as well. Anyways, so I'm going to call it BiCGSTAB, and I'm going to give it, okay, so it's going to take A, it's going to take B. This is basically the same function signature, or not basically, I think this app is the same function signature as conjugate gradients. So max iter, I'm going to default that to 1000. We're going to set an rtol that we're going to default to 1e. Let's do -6, why not? And an absolute tolerance, I'm going to set to 1e -12. Okay, those, pick whatever you want to. Okay, now we could set this up where the user gives a first matrix, a first x naught. I mean, not a first matrix, a first x naught. But we're just going to have x naught be the 0 vector. And so we're going to have x0 equals np dot zeros. Okay, and what it needs to be, it needs to have the same number of entries as A has columns. So that's going to be A dot shape, whoops, 1. Okay, initial residual, this is going to be equal to B minus A x naught. Okay, that's coming from this right here. Now it says choose an R naught star such that R naught star is equal to R naught. I'm just going to keep R naught. So wherever we see R naught star over here, I'm going to use R naught. Okay, and now we need to sort of, well, actually need a little more setup here. So the B norm is going to be equal to np Now, the reason that we're doing this, remember, is that is that we want the relative tolerance. So in other words, so essentially maybe another way to think about this is we want to have like the residual b minus ax divided by the initial residual r naught. So we want to check rm, or the norm of rm divided by the norm of r naught. Now r0 is equal to b, so that's why we're doing it here. Anyways, so b norm, let me make this norm and not that. So that is what we're going to use b norm for. And then we're going to say target. This is going to be our stopping condition, and it's going to be the maximum of tolerance and rtol times b norm. We would expect that the absolute tolerance should be smaller than this. Okay, and now we need to sort of check if we're already there, if somehow we've already made it. If the solution has to be the 0, we need to end here. Okay, this is kind of a stupid check, but I'm going to put it there. So we're going to do x naught in p dot linalg dot norm of r naught, and then 0. So this is the actually this divided by the b norm. Okay. So what we're doing here, this is the solution, the approximate solution. This is the residual, so this is the relative residual, and then divided by 0. Again, this just we're putting this here as kind of a stupid check, just in case just in case 0 happens to be the solution. This is really a ridiculous thing to have. I mean, it's not. It should be there, but also, I don't know. Maybe it's ridiculous that I'm getting that worked up about it. So j is going to be our iteration count. The only reason we have this is because we are returning the iterations. If we weren't returning the iterations, we could just have a loop that says while max iterations is greater than 0, and then reduce max iterations each time. Okay, so we need to set some things up. J is going to be equal to 0. R naught star is just going to be equal to R naught, so I don't need to do anything with that. But I'm going to set P is equal to R0, and I'm going to set rho. Okay, so if I come over here, rho, what is rho? Rho is going to be equal to R0 times R0 star, or just R0, R0. Like that. Okay. J is equal to 0, so I'm going to do while J is less than max iter. And I'm going to check each loop. I'm going to in each loop, I'm going to check the residual. And if the residual, or if the relative residual is less than what I want it to be, then I'm going to stop. So well, okay, we'll talk about that, the exact formula, when we get there. Now I'm just going to look through my formulas here. So A is going to be equal to the current value of rho divided by, and it's going to be AP dotted with R naught star, which is just R naught. So notice I have to keep R naught. I can't, I can't just say R is equal to something here and then reuse it down here, because I have to hold on to R naught, because that is my R naught star, and we use it throughout here. Okay. And the at operator is kind of magic. It knows what it should do. So AP and then R naught. Okay, so that's going to give me my A. And then my intermediate update. So notice if you look at RJ plus 1/2, that's the intermediate. From the RJ plus 1/2 to here, we're only using RJ plus 1/2. So you might think that you need to come up with a new variable for like an intermediate, but notice that whenever, after we set RJ plus 1/2 here, whenever we use a residual here, it's all RJ plus 1/2, RJ plus 1/2, RJ plus 1/2, RJ plus 1/2. Oh no, here, not RJ plus 1/2. Here's RJ plus 1/2, RJ plus 1/2. But this is when we are now getting a new RJ. So we can just say R is going to be equal to R minus A times AP. Okay, now W is going to be equal to this fraction. So let's see, here and here, and the top, bang. Okay, I don't know why I said bang. Okay, so we're going to have AR there, and then just R there, and then in the denominator it's going to be AR. So we'll have AR there, AR there. Okay, that looks right. That was W, wasn't it? And so now we're on to our update for X. So X is going to be equal to X plus A times P plus W times R. So by the way, I just want to point out, this is not, I coded this before, and when I coded it before, it was not giving me as helpful suggestions as it is now. So I just want to point that out. I don't know why, but there we go. Okay, so now for R, let me make sure I did X correctly. I feel like I made a mistake there. X is equal to X plus AP plus WR. Yep, okay, that's okay. And then R is going to be equal to R minus W times AR. Okay. Now we're going to have our new row. So we're going to have to do something here, because if we look at beta uses both the row J plus 1 and row. So first I'm just going to say row S for the row that I'm going to save is going to be equal to row. And then now I'm going to say row is equal to the new value of R, and then dotted with R naught star, which is just R naught. And then B is going to be equal to, wait, what? Hold on a second. Huh. So in my code that I did before, I see that I made a mistake. I'm not making that mistake here. I just want to make sure that, yeah, so row save is going to be equal to the old row. Then I update row. Then B is going to be the new row divided by the saved row. By the way, if you see that I've made a mistake, as always, I will find it out as soon as I try to run this. Okay, and then P is going to be equal to R plus B times P minus W times A times P. Okay. And that was one iteration, so I really need to update my J here. Okay, so now I'm gonna look at I'm gonna investigate my R. So if np.linalg.norm is less than target, so notice what's happening here. Target is basically rtol times bnorm. So what we're doing here, if np.linalg.norm is less than target, it means the residual divided by bnorm, that is the rm divided by bnorm. Bnorm is the norm of B, which in this case is the norm of R naught. So this check right here is saying if Rm divided by R0 is less than Rtol, then we need to quit. And this is actually, see, I don't like having break statements, so I just like having it like this. Okay, so sorry, there's some time there. So let me test this now. So I'm gonna run this. Okay, we see it does pretty good. I mean, like a little questionably good. I think these matrices are unreasonably well behaved. I think this matrix, especially the way that the code is, makes it a little bit too sparse. Yeah, I'm not. Yeah. Anyways, so these are maybe very nice matrices, because what we're doing here, this turns out to be a 1000 by 1000 matrix. If I make this bigger, we still get extraordinarily quick convergence, and you can check the convergence, like if you use BiCGSTAB in SciPy, it also converges quickly, even a little bit quicker than this. However, I just added this build operator that we had. So I added that, and I'm gonna show here. Okay, I'm gonna make the max iterations go to 1000. So this is 32. It's going to be a 32 squared by 32 squared matrix, so 1000 by 1000 matrix as well. So when we run this, notice what's happening here. It takes all 1000 iterations, and we get these error that are not as good. So if I increase this up to 10,000 iterations, okay, we see that it's still going to it converges, but it goes up to 1,699 iterations. We're going to come back to this when we look at preconditioning and make this go a little bit better. Anyways, so this shows just how the same method can give vastly different results for the same or for different matrices. Okay, I'm actually going to I'm going to keep things like this. All right, so the next method that I want to implement is going to be, let's see, hold on one second. Let me find the other one. So the next one I want to implement is going to be the conjugate residuals. So the residuals are going to be a conjugate. Okay, and again, whoops. This is a PDF that I uploaded. And so if we scroll through the derivation right here, this gives us the main update, or the main algorithm. So let me put this back like I had it before. Okay, and so now what we're going to do is we're going to look at a conjugate radius, or not conjugate radius, yikes, a conjugate residual algorithm. Okay, so this first part here is basically going to be the exact same. All of this beginning part is going to be the same. So I'm just going to copy and paste that. Instead of BiCGSTAB, I'm going to call it CR for conjugate residual. Now, for conjugate residual, the matrix has to be symmetric. Okay, so A must be symmetric. That is part of the derivation here. Remember that conjugate residual is to GMRes what something like conjugate gradient is to FOM. So the idea is that the recurrences can be made a lot shorter if the matrix is symmetric. Otherwise, if the matrix isn't symmetric, this doesn't make any sense. Okay, so here's what we're gonna do. I'm gonna follow along with the algorithm listing here, or sort of the algorithm. I'm gonna start with J is equal to 0. R is going to be equal to R0. P is going to be equal to R0. And then X is equal to X0. I'm not going to forget to do these things this time, hopefully. We'll see what other mistakes I make, though. There are so many different mistakes I can make. It's kind of exciting. While J is less than max iterators. We're going to do the following. Okay, we're going to do our updates. So we're going to do update our J. Max iter. I don't have an S. Shouldn't have an S there. Okay. And then we're going to do our A next. So actually, one thing that should be noted here is I'm doing a whole bunch of matrix vector products. So A times P, I do it once here, then I think I use it a few other times. Yeah, I have A times P here, A times P here, and same thing with A times R. I really should have just done A times P and saved it. So I'm going to do something similar here. So I'm going to say AR is equal to A times R, and then I'm going to say, actually, I'm going to do capital A to remind myself that it's matrix here, and then I'm going to say AP is equal to A times P. Okay, and so now my update A is going to be equal to R dotted with AR divided by AP dotted with AP. My new X is going to be equal to my old X plus A times P. My new residual is going to be R minus A times AP. B. So by the way, at this point right here, I should check There's another issue with the way that I'm coding this algorithm and the previous one. Let me type this next line, and I will tell you what that is. So B is going to be equal to so let's see, AR B is ARR, so that's the new the new R that I'm computing there. But for this old one, it's going to be ARR. So I can just do ARR. So I don't have to do that thing where I saved it before. Now, of course, as you are probably observing here, I'm doing AR again, and then I'm on the next loop. I'm going to compute it again. So maybe we can fix that, or maybe we'll just leave it like it is for now. And then we're going to say P is equal to R plus B times P. Now I have this AP here. You know what? I should do this. Hold on. AP. I'm going to change this a little bit. Is equal to AR. Actually, let me do it like this. I'm going to change this a little bit now that I see what's happening. AR. Nope. Let's do this. AR. Gosh, no, don't want that yet. Okay, and then AP is going to be equal to AR plus B times AP. Okay, and now I don't need to do these updates here, so why is that? I will need to do it outside of the loop here because they haven't been defined yet. So AR is going to be equal to AR, and then AP is going to be AP. P is equal to R, so this, I could have done it. I could have just had it how it was there. And now when we come in the loop, it's going to be everything that it needs to be. Now, what's going to happen down here? And then here, this. So okay, let me keep it like this for now. Here, let me do it like this. AR save is going to be equal to AR. I'm going to do AR save here. And now I'm going to compute AR up here. Okay. This is now making me a little bit nervous. Probably what you should do is just do this first. There's another issue here. Do this first without trying to make things where you're doing as few vector computations as possible, and then come back and try to change it like I'm doing here. Notice that this R is the old R, so I need to do RS is equal to R, and so we're going to have that here. And then P, this will be correct, the new R, plus B times the old P. And then AP is going to be the new AR, which is what we have here, plus B times the old AP, and that's good because we haven't updated that yet. Okay, so that should be the correct algorithm. All right, so I'm going to come here, and I can make this a little bit bigger now. Okay, so this is CR. I'm going to test it on the A1, and the only, it's the same function signature, just a different name, so all of that should be the same. I'm going to go back to making this 10. Let's see where I made some mistakes. You know what? I never did any return statements here. Wow. Okay. If. There we go. Let me do this. R norm is equal to this. R norm and then if we're here, we have gotten through at least one loop of the algorithm, so this will be okay. What other mistakes have I made? Oh, none. Okay, well, I've done something, because this is not correct. This does not give me the correct answer here. Okay. I knew I shouldn't have gotten fancy. Okay. This is just, you get to see Robert experimenting. Alright, so AR is equal to AR. Let's just make this less fancy, slightly less fancy. Okay. And then A is going to be RAR over AP. X is X plus AP. R is R minus A times AP. Let's forget about this for now. Yeah, let's forget about this. And let's forget about this. I do need to save this RS though. So B is going to be A at R. Oh, you know what? Here's a no. That's right. Okay. A at R. AR with R. That pairing, and then this is going to be the old R. AR and RS. Okay. RS is equal to R. It's the old R. Then P is going to be equal to R plus BP. And now AP is going to be equal to, well, that's just, okay, we don't have to, we can keep this and just compute it on the next thing. Okay. Shoot. Well, there is still a problem. This should not be happening. All right. Okay, here's what I'm gonna do. Okay, so A is equal to R paired with AR divided by AP paired with AP. That's what we have here. That's there. Okay. Then X is equal to X plus AP. R is equal to R minus A times AP. I'm going to call this RR. Is actually, I'm going to call AR at R. And I'm going to do it up here. Okay. And now here, I'm just going to divide by RR. That's going to be B. That is I hope, just a cosmetic change. Then then P is going to be R plus BP. Okay, let's try this. There we go. So I'm not exactly sure what I did differently there. But that does exactly what we want. We see it's running a little bit. Well, sorry. You know what? You know what? Oh my goodness. I'm surprised that it's working now. Because remember, A must be symmetric. So, ay. All right. I'm gonna get it together one of these days. So I'm gonna say A4 is equal to A1 plus A1 transpose, and then I'm gonna say B4 is going to be equal, so I'm going to do X4. X4 is equal to X1, and then B4 is going to be equal to A4 times x4. Okay, sorry about that. So now for CR, we're going to have A4 and B4, and down here we're going to have a 4. Okay, and again, this is more along the lines of what I would have expected. I'm going to do this with A2. Oh, I need to make all of these 2s as well. Okay. Yeah, and here we can see it runs even better. So the other matrix, I think this matrix is close to being symmetric because it's a PDE matrix. As we've seen, like the sparse structure is going to be symmetric. But this is just random. So it's not, even the sparse structure is not symmetric. And so we're going to have a different, let me back up. This matrix is close to being symmetric. Okay, that's why when I ran it on that before, when I ran the conjugate residual on that before, it worked well. In this case, it would be sort of like an incomplete GMRes method, which might work well, as we saw. I think because this matrix is close to being symmetric. Now I'm doing it to this matrix, but I'm making it symmetric by doing A2 plus A2 transpose. That's going to give a symmetric matrix. Okay. And so now on an actual symmetric matrix, we can tell it's running a lot faster. Because if you remember when we had down here, when we ran the CR with just a straight A1, like when we had this with A1, it was working, okay? It was working, but it was doing a few more iterations. Okay, 19 iterations and not getting as good convergence. So the reason that it's working is because this is close to being symmetric. Okay. All right, and now we can come down here. Let's see what happens if we run it. This is not a symmetric matrix, so I'm gonna do this. I'm gonna do CR here. I'm gonna do A5. So A5 is gonna be equal to A3 plus A3 transpose. X5 is going to be equal to X3, and then, X3, and then sometimes those things are not very helpful, is going to be equal to A5 at X5. There we go. So we're going to do the 5s down here. Okay. And we can see that it goes faster. The for the the A3 matrix is not symmetric, but the A5 matrix is symmetric, and the BiCGSTAB goes faster on the symmetric matrix there. Or sorry, the conjugate. I keep wanting to say conjugate radius. I don't know why. The conjugate residual goes a little bit faster because we're dealing with a symmetric matrix, which is going to have a nicer structure. Okay, so anyways, I have shown you two different sort of conjugate gradient variants. One is a conjugate gradient variant that doesn't require that the matrix be symmetric. This is the BiCGSTAB. And then the conjugate residual requires that the matrix be symmetric. This is kind of like if you apply the same principle. If you apply the Lanchouse principle that we did to FOM, if you apply that to GMRes, and then from there go like a D-Lanchouse, and then from there convert that to like a conjugate gradient, that's sort of the same, along the same lines that you can go to get a conjugate residual. And you can read the notes that I gave that show, you can read my notes that I posted that gives this derivation. Anyways, in the next lab video, I'm going to show you how we can precondition these matrices. Well, I'm going to show you how we can precondition GMRes and BiCGSTAB.